Just having a look today at this double bent axis pump assembly off a Hitachi EX200 or 220. This would be sort of -2 series. So this would be maybe typical of a 790E John Deere excavator as well. So we're kind of going back to the 1990s here. But significant pump because it was a design that was one of the first sort of full authority electronically controlled excavator pumps in the marketplace, and you know, with a high population, of course. And we'll look at these solenoids that of course control the displacement of the pump and are outputs of a computer on the machine called the pump and valve controller, or PVC. Basically two bent axis pumps inside here, inside this common housing, and then we've got a gear pump here that's going to be our supply for the pilot system of the machine for the servo control and the joysticks, etc. in the cab. As well, this gear pump, fixed displacement pump, is going to be the supply through this steel line to our solenoids and our actuator that's going to control the displacement of these bent axis pumps. Now I've also got a cutaway here of this pump assembly for training purposes, so we can see inside how the pumps are driven and how they turn and how the displacement is changed. We've got some gearing inside here that's going to get the pumps counter rotating. Directly driven from the input shaft. We've got power coming into this pump assembly, and then a set of helical gears here driving the other piston pump in counter rotation. And this one's been machined open so we can see inside the barrel how the pistons sit in there. And then we've also got a gear driving our gear pump as well. So gear train built into the pump that's going to make sure all three pumps are turning. And then let's have a look at how the displacement's actually going to be controlled here. So on the front side of the pump, basically in line with this supply fitting, in this part of the housing is a actuator, which looks a lot like a double acting hydraulic cylinder, and that's effectively what it is inside here. That actuator is hydraulically controlled. Oil pressure underneath here in this part of the cavity is going to drive this piston up. Oil pressure on top, it hasn't been cut open that far, but oil pressure on top of this actuator will drive it down. And then in this hole right here, you can see there's a pin in there. You can see the end of a pin. If we go around this side and look through the cut here, I think we'll be able to see, yeah, there's that pin coming through a double port plate assembly. If I can get the light on this a little better. So right, put my laser pointer on it if I can. Can I? Yeah. So right down in there, there's that pin, is the pin coming through from the actuator and driving the port plate. So this is a variable displacement piston pump, but it's not an axial type or inline type. This is bent axis. So what's going to actually move to change the displacement is that double port plate assembly. And this generation of pump had one long port plate that takes both barrels closer to the axis of the shaft coming into the pump to reduce the displacement, or bends it down further to increase the stroke length of the pistons relative to the barrels. And the manual says that in normal operation that port plate is going to change from about 2 degrees of bend from the axis of the shaft, which would be horizontal here, to about 24 degrees of bend, which would give us our maximum displacement. So when you look at a bent axis pump housing, you kind of see a bit of a bend in the shape of the outer housing, and that reflects the displacement change that's going to happen within. On this one I can actually pry the actuator up and down, and we can look at how that displacement changed. So right now that actuator is in the full up up position. So if hydraulic oil is sent by the control solenoids underneath here and drives the actuator up, that's going to reduce our displacement of the pumps. And then if oil pressure on top controls the port plates, I'm just going to pry it down here externally using the port plate down to our 24-degree position with that actuator at the bottom. That will give us more stroke length. You can see the bend of the axis relative to the pistons and the barrels. It's going to give us more stroke length as the rotation happens throughout 360 degrees in this pump. So where we're positioned now, it's also evident when you look in here at the drive gear in the pump that we're actually driving the pistons with the engine, and the barrels are kind of a passive receiver of that rotation. So the pistons rotate, driving the barrels around, opposite to what we'd have with a axial piston pump, where the barrel would be splined and the barrel would be driven and the pistons would be taken around by the barrel. This one, the barrel's taken around by the pistons. And then with that stroke length, you know, at the top here, I can probably see, well, maybe 1.25 inches of piston sticking out. At the bottom, the pistons are actually recessed back into the barrel, so we probably have almost 2 inches of stroke length at this full 24-degree full displacement position. So it's the actuator that moves the port plate up and down, and the port plate assembly that I can see the edge of in here, it's going to affect the barrels. And the barrels have a center pin to sort of keep them in alignment with that port plate as they travel, and there's a spring in there that spring loads them tight into position. So that's how displacement is going to change and change the output of the two pumps. And of course, in this generation, again, that port plate's one long component across there driven by one actuator. So we can't have independent displacement from these two pumps. They're going to be the same displacement between 2 and 24 degrees of bend, and the flow rates are therefore going to be the same out of the two pumps if they're both in good condition. And what can be different, however, theoretically, is the pressures. You know, in this cutaway, we can see the porting, but if I look at the porting on the non-cutaway pump, you know, here's the suction port where the line would connect from the tank, bringing oil into all three pumps, actually, the two piston pumps and the gear pump. And then I've got a discharge from what might be called the rear pump, and then I've got a discharge port from what might be called the front pump. And theoretically, these two pumps could then be working at different pressures if they were feeding different sections of the control valve or different control valves. However, if we go look at the schematic on this machine, we'll see that actually, if you follow the lines out of those two pumps, they actually come into the control valve. In this generation of machine, they actually connect together within the control valve of the machine. So really the two pumps on this Dash 2 series machine really just work like one big pump. So nothing really can be different. The flow is going to be the same here compared to here. The pressure here is going to be the same as the pressure here because the hoses at the other end are basically effectively joined together. So again, you can see the porting here on the port plates, the discharge ports coming out here through this passage painted red, leaving that pump. And on this guy, again, you can see how the port plate is connected into this chamber, and there's the discharge. And then there's a pressure sensor here in this port, measuring the pressure at the output of this pump, which would effectively be the same as the pressure here. So we really only need one pressure sensor to measure the pressure of both pumps, because they're going to tie together in the control valve anyway. So it's impossible to have two different pressures in a hose that's connected to the other one. So there's a pressure sensor, and that's our first look at an input to the pump and valve controller that's actually going to be used by the computer and the software to influence the displacement of this pump and effectively then control the solenoids here that are going to change the displacement. So that's part of our full authority system. The other sensors that the computer is going to use, there is a speed sensor here watching the gear teeth go around. Some excavator manufacturers would put that speed sensor in the flywheel housing. My guess as to why it's in the pump on this unit is because, you know, in a John Deere excavator or Hitachi excavator, we've got different engines with different tooth counts on the flywheel. So they're going to watch the teeth on this gear and use that as a speed sensing input. Hitachi calls this the N sensor for number of revolutions per minute, I assume. And then right next to that, we've got an angle sensor. So this is a position sensor that's connected to a fork inside here. And that fork, you can see it inside the housing there. Get the light on that properly. It's tricky to do. So there's a fork you can see in there that runs down and fits over a pin on the port plate. So that big double port plate assembly, as it moves from, you know, 24 degrees of bend up to 2 degrees of bend and back and forth into different positions, that fork is going to move this rotary position sensor and change the voltage signal on the third pin here back to the pump and valve controller. So this, I believe it's a 5-volt reference, and somewhere probably between 0.5 volt and 4.5 volts is going to tell the pump and valve controller where that port plate is, and therefore the displacement, if it's calibrated properly. I assume it has to be calibrated. So we've got a speed sensor, displacement or angle sensor, and then we've got a pressure sensor as well. So those three inputs go back to the pump and valve controller. If you take your speed of a pump and multiply it by the displacement, of course we get the flow rate. So you're getting a theoretical flow rate that the pump and valve controller can compute to know the liters per minute or gallons per minute out of the pump. And then if you multiply your flow rate by pressure and divide by a constant, you get hydraulic horsepower. So that's how the ECM on the machine knows the hydraulic horsepower load of the pumps. With a slight, variation, a slight unknown, it doesn't know the load for the gear pump or pilot pressure, but that's relatively low amount relative to what the horsepower of the main pumps could be, the piston pumps. So with the pump and valve controller knowing that, and within its software knowing the engine horsepower, theoretically again, it knows how to control the displacement. And then these two solenoids, again, are outputs of the pump and valve controller, and they're going to command upstroke to increase displacement or destroke to decrease displacement to match effectively the hydraulic horsepower of the hydraulic pump to available engine horsepower, which is sort of the goal on every excavator, because without some type of control for displacement, of course, at full flow and pressure, the pumps would be asking the engine for far more power than it has. Generally, 2 or 2.5 times engine power is capable request of these pumps without some type of management of the displacement. So on more primitive systems, we're just dealing with springs and fixed rate of compression of springs. But on this machine, the computer's watching the three sensors: speed, position, and pressure, and then commanding the two output solenoids to change the displacement and give us our match of engine power to hydraulic horsepower. So the pump would be at maximum displacement when our pressure requirements are low in the system, because high flow and low pressure multiply out to a relatively low horsepower number. And of course, as the pressure goes up, as would be sensed by the pressure sensor here, then the ECM is going to know that you can't have maximum displacement, so it's going to start to de-stroke the pumps, and it's going to do it via these solenoids and the hydraulic actuator that's going to move the port plate or valve plate within the head. So that's kind of the logic between these pumps and how they're constructed. And then in the manual, there's typically some instructions about what to do if your computer fails. Let's see if I can stumble across it in here. Generally, there's a computer failure mode or a limp mode that will tell you what to do if your computer fails. So here it says computer failure mode, and they're showing us taking the bottom plate off underneath the actuator. They actually show the actuator out, but what you'll notice on this cutaway, oh, I moved it down just one sec. So in here on this plate underneath the actuator, there's sort of a hexagonal piece that sticks up from this plate as part of this plate. And in the normal operating position, that fits through a hole in the actuator that creates a space of cavity in the actuator that clears that stopper. But if you have a computer failure, what they tell you to do is take this plate off the bottom, rotate it 180 degrees and reinstall it, and then that hexagonal stopper will come up and hit the actuator and drive the actuator to about the middle position. So you'd have to be about half displacement, which would allow you to limp the machine back to the shop or onto a float, or even theoretically keep digging with half displacement. The issue being, if you didn't have the ability to override that displacement control mechanically, the pump would want to stay at maximum displacement 24 degrees of bend, and of course if you were trying to load the machine or on a float or something, you'd be continually stalling the engine, asking for full displacement regardless of pressure. So that's how this computer failure mode basically would work. So that's basically the operation of the pump. The last thing I want to talk about, just to finish this off, I just want to talk about this plug on top of the housing here. And this extends beyond this model of excavator and this pump, but this housing is a flooded housing. So you won't find a case drain line coming off the top of the pumps like you might on some excavators, because when the suction line is connected here from the tank, it's not tightly sealed to the suction ports of the port plate inside. So basically the whole housing of the pump becomes part of the tank, which is good because we've got some tapered roller bearings and gears and things in here, and of course all the rotating assembly of the pump needs lubrication. And also the gear pump, the pilot pump, is going to draw its oil from the case. It doesn't have its own suction line from the tank, so it's drawing out of the case in here. So the whole housing of the pump is basically part of the tank. And then if you look at this pump installed on a machine, you'll find that your hydraulic oil level of the tank is generally higher than the pump housing. You know, the sight glass may be, mid-range might be here. So when you do a 2,000 hour service, or you're draining the hydraulic tank for any reason on this machine, you're going to be draining the oil out of the pump housing as well. And then when you refill the tank, there's a tendency for air to get trapped inside the pump housing, and it's not going to want to purge itself naturally. So during a 2,000 hour service, most manufacturers of machines with this style of pump will tell you to loosen the threads of this plug after you refill the tank. Make sure you hear all the air hissing out of there and get some clean oil coming out the threads, and then tighten up this plug to make sure you basically burped the air out of the housing so you don't destroy the gears and bearings and of course rotating groups of the pump assembly by running them dry. So follow the operation and maintenance manual for your machine during a service. And again, that extends to most hydraulic excavators that have some sort of process of ensuring that the pump housings aren't dry after changing the hydraulic oil. Hope that helps.